Hello! In this video, we are going to prove the following theorem. Let xn be a sequence of real numbers with starting index m. Suppose k is an integer greater than or equal to m, and x is a real number. Then the sequence xn with starting index m converges to x if and only if the sequence xn with starting index k also converges to x. So, as you can imagine, the sequence xn with starting index m looks something like this. Right, essentially starts at xm, then xm plus 1, then xm plus 2, and so on and so forth. Since k is greater than or equal to m, certainly we have the sequence xn with starting index k. The only difference between these two sequences is that the sequence with starting index k is going to start at some later point than the sequence with starting index m. And because that's the only difference between these two sequences, we should expect them to converge to the same value, if one of them converges at all. And so that's really what this theorem is saying. And so we're going to prove it. The whole goal is to prove that this guy converges to x if and only if this guy converges to x. But before we get into the proof, what does it mean by definition for these sequences to converge to x? Well, by definition of convergence, to say that this sequence converges to x means the following. It means for every epsilon greater than 0, there exists an integer capital N greater than or equal to the starting index m, such that for all n greater than or equal to capital N, the absolute value of xn minus x is less than epsilon. Similarly, to say that this guy converges to x means the following. It means for every epsilon greater than 0, there exists an integer capital N greater than or equal to our starting index k, such that for all n greater than or equal to capital N, the absolute value of xn minus x is less than epsilon. Okay, so now let's get into proving this statement. Now we're trying to prove this is true if and only if this is true. And to prove that, we're going to prove if this is true, then this is true. And then we're going to prove if this is true, then this is true. Let's start out by proving the forward. And so to prove the forward, let's suppose that the sequence with starting index m converges to x. The whole goal from here is to prove that the sequence with starting index k converges to x, which means we want to prove that this second statement is true. And since we're trying to prove a statement about every epsilon greater than 0, let's give ourselves an arbitrary epsilon greater than 0. The whole goal is to find an integer greater than or equal to k such that this is true. Now, since we know that the sequence with starting index m converges to x, this means we are given that this first statement is true. And this first statement works for every positive real number. So in particular, it must work for the positive real number epsilon that we've just introduced into our proof. So taking epsilon to be the epsilon we just introduced into our proof, we have that this is true. So there exists an integer, capital N, greater than or equal to m, such that for all n greater than or equal to capital N, the absolute value of xn minus x is less than epsilon. Now, we could call this integer anything, so I'm actually going to call it capital N prime. Now remember, the whole goal is to find an integer greater than or equal to k such that this is true. Well, the claim is that if we take this integer to be the maximum of capital N prime and k, then this statement will be true. So let's define capital N to be the maximum of capital N prime and k. Now, this is a valid choice for capital N, because since capital N is the maximum of capital N prime and k, this means that capital N is greater than or equal to capital N prime and greater than or equal to k. So yeah, capital N is greater than or equal to k, which means we have a valid choice for capital N. So with this choice of capital N, we proceed to show that this statement is true. And since we're trying to prove a statement about every integer greater than or equal to capital N, let's give ourselves an arbitrary integer greater than or equal to capital N. Call it N. From here, we want to show that this inequality is true. Well, since capital N is greater than or equal to capital N prime, certainly N is greater than or equal to capital N prime. Well then, we know that this statement is true. And this statement works for all integers greater than or equal to capital N prime. So in particular, it must work for the n we have here. So taking n to be the n we have here, we have that this inequality is true. And so we have shown that this inequality is true. And therefore we have proven this statement. So the sequence with starting index k converges to x. So at this point, we have proven if this is true, then this is true. Now we're going to prove the other direction. We're going to prove if this is true, then this is true. To do that, suppose this is true, right? We're supposing that the sequence with starting index k converges to x. From here, the whole goal is to prove that the sequence with starting index n converges to x, which means we want to prove that this first statement is true. And since we're trying to prove a statement about every epsilon greater than 0, let's give ourselves an arbitrary epsilon greater than 0. From here, we want to find an integer greater than or equal to n such that this is true. Now, remember, we know that the sequence with starting index k converges to x, which means we are given that this second statement is true. And this second statement works for every positive real number. So in particular, it must work for the epsilon we've just introduced into our proof. So taking epsilon to be the epsilon we have here, we have that this statement is true. So there exists an integer capital N greater than or equal to k, such that for all n greater than or equal to capital N, the absolute value of xn minus x is less than epsilon. Now remember, the whole goal is to find an integer greater than or equal to n, such that this is true. Well, the claim is that if we take this integer to be the capital N we have in our proof, then this statement will be true. Well, notice, since k is greater than or equal to m, certainly capital N is greater than or equal to n. So our choice of capital N is greater than or equal to m. That's what we have here. So now all that's left to check is that this statement is true. Well, actually, we already know that this statement is true, right? That is actually right here. For every integer n greater than or equal to capital N, the absolute value of xn minus x is less than epsilon. So this statement is already true. So we're done. This entire statement is true, and therefore the sequence with starting index m converges to x. And so at this point, we have proven both directions of the if and only if. So we have proven this entire statement. And so this completes the proof. Now, what this theorem is essentially telling us is if we're given a sequence of real numbers, and we know that that sequence converges for a specific starting index, then if we increase the starting index, then the same sequence will converge to the same value. To see a concrete example, let's consider the following sequence. We know that this sequence converges to 0, right? We've proven this in a video in the past. But if we change the starting index of this sequence, let's say the sequence goes from n equals 17 to infinity, this sequence will also converge to 0. And that is exactly what this theorem is telling us. If we change the starting index of our sequence, then it will converge to the same value. Now, what this means is if we want to express this in a different notation, well, the notation we usually use is like this. The limit as n approaches infinity of 1 over 2 to the n is equal to 0. But which sequence are we referring to? Are we referring to this one, or are we referring to this one? it doesn't matter because they both converge to 0, right? We don't have to specify the starting index in this notation because no matter what the starting index is, this sequence will converge to 0. And so that's essentially what's going on here. Let's look at another example that involves infinite series. An infinite series you might be familiar with is this one, right? The sum from k equals 1 to infinity of 1 over k squared is equal to pi squared over 6. Now, what does an infinite series mean by definition? Well, actually, what's going on here is we are considering the following sequence. The sequence 1 over n squared from n equals 1 to infinity. And from this sequence, we can construct the following sequence of partial sums. Right? We can all agree, since this sequence exists, certainly this sequence exists. Right? The first term of this sequence is 1, therefore the first term of this sequence is 1. The second term of this sequence is 1/4, therefore the second term of this sequence is 1 plus 1/4. And the third term of this sequence is 1/9, therefore the third term of this sequence is 1 plus 1/4 plus 1/9, and so on and so forth. We have a sequence of partial sums. Now, if this sequence of partial sums converges, then the notation we use to express the value it converges to is this notation. Right, so the limit of this sequence, we express it in this notation. But remember, it doesn't matter what the starting point of our sequence is. So we could change this from n equals 1 to n equals 2. As you can imagine, it's going to converge to the same value. If we change it to n equals 17, it'll still converge to the same value. And so, unambiguously, we can just write this as follows: the limit as n approaches infinity of this sequence of partial sums. We don't have to refer to the starting index. So that's essentially what this theorem is telling us. We don't have to worry about the starting index when asking what value the sequence converges to. If it converges for a specific starting index, then it's going to converge to that same value for any starting index. And so yeah, that's pretty much it for this video.